Okay, now we're going to talk about high spatial resolution sensors. So these are kind of well, I think of it as a relatively recent development. The Land Remote Sensing Policy Act of '92 allowed the licensing of these satellites. Before that, it was considered national security risk to have people looking at things at too high a spatial resolution. ICONOS was the first U.S. commercial satellite. ICONOS 1 was launched in April 1999. That was lost in space. ICONOS 2 was launched in September 1999, and that's the first we have data from. These sensors in general follow the same pattern, which is they have a panchromatic band and then a multispectral suite of bands. The multispectral suite of bands has a spatial resolution that's 4 times, well, the spectral resolution is 4 times that of the panchromatic band. So if the panchromatic band is 1, then the multispectral band is 4. These are all in sun-synchronous orbits, about 10:30 a.m. overpass locally, and they have a repeat coverage of about once every 3 days. In general, the entire satellite can be turned so that you can do off-nadir pointing, either for collection of stereo coverage or for fast collection of a scene in an area that there's some kind of time-sensitive need to pick up an image. And these systems do not, as a rule, collect data everywhere all the time, like something like Landsat. They are they collect data basically where they're paid to collect data. You send them an area of interest, and they send you a quote. And if you accept the quote, then they're going to look at that area the next time that the satellite comes around. So here's a variety of different sensors that fall into this characteristic of very high spatial resolution sensors. The spectral resolution, again, it follows, one of 2 patterns, a panchromatic band and then a blue, green, red, and near infrared band. The panchromatic band, second column, will generally have 1/4 the pixel size of the multispectral band. And that's because if you're looking at the whole suite of the panchromatic, which can either be all the visible or all the visible and the infrared, you're just observing more energy than you would be if you were looking multispectrally. And so because you have more energy, you can have smaller pixel sizes in the detectors that actually record the image. And so that's why you get this 1 meter, 4 meter, or 0.6 meter, 2.4 meter. One of the lower resolution systems in here is Rapid Eye. Rapid Eye was full coverage. It no longer runs, but it was full coverage at 5 meter spatial resolution, and I personally miss it because I thought it was a good. It added flexibility that you wouldn't otherwise had from the other suite of systems. And they create beautiful images, right? So like here's the Eiffel Tower, here's the Millennial Ferris wheel. I forget what they call it. It's in London. And this gives you an idea on the left of the highest spatial resolution systems from aerial photography, and then sort of a 1 meter spatial resolution fused panchromatic multispectral image, and then Landsat on the right. And you can see your satellite data product there looks a heck of a lot like your aerial photography product. And so that's one of their real strengths, is you can use them in a photo interpreted context. Digital Globe has the most of these satellites. Um, so their satellites come under the word QuickBird, WorldView 1, WorldView 2, um, and they also do aerial data collection. And Digital Globe is actually right down in Longmont. So they actually hire a great number of remote sensing scientists. Worldview 2 is an exception to the rule here. And this is a Digital Globe product. You know, QuickBird follows the general rule, which is it's got a panchromatic band from 450 to 900 nanometers. It's got blue, it's got green, it's got red, and it's got near infrared. Worldview 2, on the other hand, puts in a lot of interesting things. It puts in a coastal blue channel that allows you to do better atmospheric correction for the blue band, but also penetration into water that's better than in the blue, and adds a near infrared 1 and near infrared 2, as well as a red edge band. So that red edge band gives you information about how fast the low reflectance in red increases into the near infrared for vegetation. And so that's a vegetation health indicator. And it's got a revisit frequency of every 2 to 3 days, and can off nadir point plus or minus 30 degrees nadir. So this is a very sophisticated system. Worldview 3 is even more interesting because it adds in 8 shortwave infrared bands. So it's got a panchromatic nadir band at 31 centimeters, a multispectral at 4 times that, or 1.24, and then it's got a shortwave infrared nadir at 3.7 meters. So I guess that's what, yeah, about 3 times the multispectral pixel size. That is a very forward-thinking design, because most systems that do away with the shortwave, and this allows you to have more information about the things we've talked about, soil moisture, and it also allows you to match up better with Landsat. So all in all, a very sophisticated design. Rapid Eye, these were 5 sun-synchronous Earth observation satellites, so large area, multispectral images, frequent revisits with high spatial resolution, 5 meters, which we found was adequate for photo interpreting fire damage at the High Park fire. There's a beautiful image from Rapid Eye. And another is an agricultural landscape. So the advantages of high spatial resolution, or some people would say hyperspatial data, well, it's high spatial resolution, and it comes with multispectral imagery as well, and it's the highest resolution data ever available to the civilian mapping community. It has high radiometric resolution, so that allows you to get at differences in things like forests where they're going to be dark, and so you can really use that extra radiometric resolution. It has high location accuracy, and you can buy orthorectified images from the various providers, so it's ready for input into GIS. It's familiar, it can be interpreted like aerial photography, although it also, for the most part, can be interpreted using conventional digital imagery techniques. You can get timely imagery, that is, you don't have to wait 16 days to get an image. You can, if you can pay for it, you can get an image generally in 1 or 2 days, particularly if you're not very specific about what sensor you need the data from, something will be passing over. And as we'll talk about, Planet Labs as a solution that's distinct from this one that can get you images the same day if you need them. Repeatable acquisition, so it's possible to get images that are taken from the same time of day, from the same place. Rapid delivery, that's one of the things they make as part of their promise to you. It has an extremely long focal length, so you can capture some terrain relief information. And some of the sensors have 4 nadir and aft looking linear CCD arrays, so push broom arrays, so that you can get in-track stereo strips. So you get one looking forward, one looking aft, and all of them have pointing capabilities. So you can generate, again, either cross-track, so from one track or path to the next, or a long track. You can either be pointing forward and then rotate the satellite so it's pointing back at the same area, and then get a stereo image that you can generate from that. Limitations, I mean, the spatial resolution is lower than aerial photography. Scheduling acquisitions at desired times is sometimes more difficult than anticipated. The US military is the biggest funder of these, of data collection from these satellites, and if you have an acquisition that conflicts with theirs, then you don't get your image. They're small images, as we'll see, maybe 10 by 10 or 20 by 20 kilometers. The view angle may vary from image to image. So if they're doing something off nadir and they're coming around and still rolling to get back to the normal nadir image, you might be able to pick up a different view angle than you would otherwise. Classification can be difficult because, rather than with something like Landsat looking at sort of an average forest condition, you're actually looking at pixels of shadow, pixels of shaded foliage, pictures of bright foliage, pictures of rock, pictures of all sorts of different things. And in a standard classification, each one of those is going to come out as a class. So it does make that more difficult. And finally, cost. I mean, it's a lot of money. It's thousands of dollars. And their criteria for a successful image is 20% cloud cover or less. So you may collect an image over an area. Your particular area of interest might be covered with clouds, and they'll say, hey, it's less than 20% clouds, and so you need to pay for it, which doesn't do you very much good. And so this gives you an idea of the coverage, what a single Landsat scene looks like on the Front Range. That's Denver there, versus Iconos. And you can see it's just, there's nothing like it. So in general, you're going to try to avoid using something like these high spatial resolution systems unless money is no object. And one approach you can use is you can subset a Landsat image with a bunch of Iconos images. Use the Iconos, say, to do photo interpretation, and then the Landsat to use classification approaches to map the entire Landsat scene. I don't know why you do that though, because you can get NAIP data that'll let you do the same thing. Some non-photo interpreted uses of this data: water quality and water clarity in urban applications. So looking for areas where you might have non-point pollution sources that are making your water either turbid or promote algal growth. You can map that very easily. Mapping impervious surface, so the amount of concrete and asphalt surfaces, those lead to increased rates of runoff, And so that's something that water and sewer agencies for municipalities want to know about. So this is an easy way to get a map of that. Mosquito control, some places have looked at using high spatial resolution data to look for puddles, essentially, and then direct people out to those points to kill off mosquitoes. We always have a problem with West Nile virus around here, so the Front Range is one of the areas where this has been tried. Precision agriculture. So here on the left, we're looking at an NDVI from an ICONOS satellite, and you're looking areas that are greener, have greater NDVI and therefore greater vegetation cover. And that information can be used to plan, say, a nitrogen application. So instead of applying the same amount of nitrogen throughout the entire area, you're just going to pinpoint those areas that need the most and therefore cut down on nitrogen pollution and, yeah, cut down on nitrogen use and cost, and also on nitrogen pollution and runoff. Marine applications, these have been very important, particularly with coral bleaching. And I want to talk about something called pan sharpening. So I've said, this high spatial resolution data generally comes with a panchromatic band that's high resolution, multispectral bands that are lower resolution because of these limitations due to the optics and the actual sensor pixel sizes. As well as to some extent the amount of data that you can collect, store, and transmit from the satellite. So you have this bundling of a 4-to-1 ratio of multispectral and high spectral resolution data. And after you've collected the data, there's a process called pan sharpening that can be used to try to reproduce a product that appears multispectral, but with the higher spatial resolution. So here's an example. The simplest way to, well, we've discussed principal components analysis, right? Where we're going to do this analysis on an image. We're going to come up with a series of bands. The first band is going to be brightness, right? So we can take a multispectral image, do a principal components analysis, and create a brightness band, and then a greenness band, and then whatever other bands are left over. We can then remove the 4-meter brightness band and put in the panchromatic band. Okay, you double up the resolution or the number of pixels of the other bands, but you essentially just insert that band, and then you back transform the PCA, and that leaves you with the original colors, but gives you the appearance of a 1-meter spatial resolution image. So on the bottom, you can see a 4-meter RGB image of various different kinds of industrial situations, and I guess some homes as well. And then right above it, the 1-meter panchromatic image, where you've used that higher spatial resolution image to sharpen it up. You're not really getting what it appears to be. As far as your eyes are concerned, it appears to be a higher spatial resolution data product. When you're actually then using these images for further processing, then you're going to run into limitations because you're just going to have edges where the brightness changes, but the spectral data doesn't really change. So that's a limitation. Finally, I want to talk about one more high spatial resolution sensor. This is a concept that's only about 3 years old, and it's putting small satellites in orbit that by themselves don't have very high capabilities, but you put a lot of them in. And the big one in this sector is the Planet Labs constellation of um, sensors, and you can see each one of them is about 10 centimeters by 10 centimeters by 30 centimeters, I think. So these are very, very small. Each one has a very basic camera on it. It is a frame capture camera. And then you can see they're wrapped in solar panels, and then they beam down to ground stations. And so the individual cameras are not very sophisticated, but you can have these going over multiple times a day. Um, so they've launched 360 of these things. There are currently 100 of them still operating. The ground sample distance, the spatial resolution is, between 75 centimeters and a meter. It's a regular frame camera with panchromatic and multispectral. They don't do any kind of radiometric corrections because they're not trying to create a high precision product. What they're trying to do is look at things like shipping lanes, parking lots, um, what do you call those things? Parking lots. Oh, precision agriculture, where you more need a relative measure of what you're looking at than any absolute precise measurement. And so they have a very sophisticated interface to this data so that you can go in and see, individual images from sometimes, depending on what the constellation looks like at any one point, sometimes you're going to be able to get, multiple images a day. More often it's, 3 days between images, provided, unlike this image, that you don't have clouds.